Good morning, students. My name is Joseph Okoth, and once again, welcome to our physics lesson. And today, we want to look at the applications of electromagnetic induction. Now, one of the applications of electromagnetic induction is in the transformers that we normally use every day. And as you can see on the board, we have two types of transformers. The first one is known as a step-down transformer, and the second one as step-up transformer. So we are going to start with the step-down transformer. The type of a transformer is identified by the type of coils in both primary and the secondary coil. If the number of coils are more in the primary coil as compared to the secondary coil, then that transformer is referred to as a step-down transformer. So on the board, what you can see is the step-down transformer. Right at this point, this is the electrical power point where the power is being supplied. It is then being channeled to this primary coil, and since a transformer uses AC current, there is change in direction of current and hence the change in magnetic field. This change in magnetic field is linked to the secondary coil, whereby we have few number of turns as compared to the primary coil. The end result here is that the current in the primary coil becomes less than the amount of current in the secondary coil. Hence, we call it a step-down transformer. This is the symbol of a step-down transformer. As you can see, we have more turns in the primary coil as compared to the secondary coil. Then down here we have what we call the turns ratio. The turns ratio is simply the number of turns in the secondary coil divided by the number of turns in the primary coil, or the voltage in the secondary coil divided by the voltage in the primary coil. The division there, or what the result there gives us the turns ratio. In step-down transformer, the turns ratio is normally less than 1. Next, we have the step-up transformer. In this case, the number of turns in the primary coil is less than the number of turns in the secondary coil. And this is the symbol of a step-down transformer. It is identified by comparing the coils in both primary and in the secondary. So here we have less turns in the primary coil as compared to the secondary coil. Therefore, this one is a symbol of step-down transformer. Now, point to note, in a step-down transformer, current in the secondary coil is greater than in the primary coil, while in a step-up transformer, current in the primary coil is greater than in the secondary coil. As you can see here, we have less number of turns in the primary coil as compared to the secondary coil. Therefore, current here in the primary coil is greater than the current in the secondary coil. These are equations involving the transformers. And as you can see, the secondary voltage over the primary voltage is equal to the number of secondary turns over the number of primary turns. Vs over Vp simply stands for the voltage in secondary and primary. Ns over Np simply stands for number of turns in secondary coil, and Np is the number of turns in the primary coil. The assumption that we are making in this equation is that there is negligible resistance among the coils in the transformer, and therefore in that case we know that power is given as the product of voltage and the current, i.e. P is equal to Vi or IV. Power input is equal to the primary voltage times this primary current. That is Pn, sometimes abbreviated as Pi and N. P input is equal to P Vp times Ip. Same applies to the secondary coil. The power output is given by voltage in the secondary coil times current in the secondary coil. Then we have the efficiency of a transformer. Efficiency is given by power output over the power input. Then we multiply that by 100. And on this side we have the symbols. This is the symbol of efficiency. Then this is the power output. Then below here is supposed to be the power input. That is voltage in the primary coil times current in the primary coil, and then we multiply that by 100. This is what we call the transformer equations. Vs over Vp, Ns over Np, and also the efficiency, which is the power output divided by the power input, and then we multiply that by 100. The equation continues. We have what we call an ideal transformer. An ideal transformer is a transformer with negligible or less resistance. And therefore, in case of an ideal transformer, the energy loss is minimal. And it's therefore given by 100 is equal to Vs Is over Vp Ip times 100. This means that there is no resistance within the transformer, and therefore Vp Ip is equal to Vs Is, and therefore current in the primary coil is given by Vs Is over Vp. Down here is the general equation again of the transformers. Current in the primary coil over current in the secondary coil is equal to the voltage in the secondary coil over voltage in the primary coil, which is equal to number of turns in the secondary coil divided by the number of turns in the primary coil. Next is an example of a problem involving a transformer, and as it reads, a transformer is to be used to provide power of 24 volts, sailing bulb from AC supply of 240 volts. Find the number of turns in secondary coil if the primary coil has 100 or 1000 turns. We simply substitute in the transformer equation here. Therefore, 24 over 240 is equal to Ns over 1000, and calculation there gives us the number of turns in the secondary coil to be 100. Another example that I want you to go and work out is the sum of the problem on the board. It says a power station has an output of 10 kilowatts at a potential difference of 500 volts. The voltage is stepped up to 15 kilovolts by transformer 1, that is T1, for transmission along a grid of resistance 3 kilo ohms, and then stepped down to 240 volts by a transformer T2 at the end of the grid for use in a school. Given that efficiency of T1 is 95% and that of T2 is 90%, find the following. 1. The power output of T1, the current in the grid, the power loss in the grid, the input voltage of T2, the maximum power and current available for use in school, and find why it is necessary to step up the voltage at a power station. Now, in all this, pay keen attention to the transformer equations that we looked at previously, and once you master them and then you master how the stepping up and the stepping down is done, then the equations will simply give you the solutions to the questions that we have on the board. Up to that point, we've come to the end of our lesson. Welcome again next time. Goodbye.